say it's a pleasure to take part in this seminar with High-Techs, and hello everyone on the line, thanks for coming along. What I'd like to do is start by posing a question, which is, how many times do you think TrustZone is mentioned in the v7 technical reference manual? Remember, that's a 2,700 plus page document. So you might think TrustZone would be mentioned many times in that document. Well, actually the answer is no, it's not mentioned at all. There are no mentions of TrustZone. So that was a huge surprise to me when I first started working with TrustZone. And what I'm hoping to do in the next 30 minutes or so is to explain what I learned during that first project using TrustZone, and I hope that's going to be helpful to anyone else who's starting to work with TrustZone in an embedded system. So I expect some of you might not know the name Pebble Bay, and I'd like to spend a minute or two explaining who we are and what we do. I promise this won't be a sales pitch, but I think it will give you some useful background for what's coming up. Pebble Bay is a specialist embedded software development company. As Raphael mentioned, I founded Pebble Bay with a colleague about 10 years ago. We work with companies building typically quite complex embedded systems, usually for industrial automation, automotive, telecoms, and defense applications. And typically our customers face problems finding the right expertise for their project, meeting tight project timescales, and sometimes tracking down performance or reliability problems. So we can help customers in all of those areas. We work on a project basis, and I recently worked on a project which used TrustZone in a system which was based on an ARM Cortex A9 processor. Actually, it was the hard processor system of a Cyclone 5, an Altera Cyclone 5 system-on-chip FPGA. And I had to pretty much bootstrap my knowledge of TrustZone from nothing at all, and I found several surprises along the way, and that's really what I wanted to try and share with everybody during this presentation. I should say before we get much further that at this point I'm certainly not an expert on TrustZone, but hopefully some of the things I've learned will be useful to you as well. So I think the first thing is probably to try and get some terminology straight. TrustZone is a term that I'm sure we've all heard, and it's actually a term that's used by ARM for marketing purposes. It's talking about a set of security extensions to ARM's processor designs, but obviously TrustZone is a much more snappy and kind of memorable name than security extensions. The only problem is that TrustZone, as I said at the beginning, TrustZone is almost completely missing from any of ARM's technical documentation. So it presents a bit of a problem if you're trying to get started. You know, how do you find out what TrustZone actually is and what it does? Well, security extensions turns out to be the thing to look for when you're reading the technical documentation. And now, one exception to that is that ARM have published a white paper which I've referenced on the slide there, which is a kind of broad description of TrustZone, and it's aimed at, I think, businesses building systems where trust and security are important, and the kind of canonical example that ARM use in their paper is a mobile phone, which, you know, you might argue it's not really an embedded system, so it doesn't immediately make you feel comfortable that you're in the right world here. But anyway, that white paper has this excerpt that tries to define or describe what TrustZone is. And as that white paper says, TrustZone is a framework. It's not a complete solution in itself, but it provides kind of scaffolding that can be used by both hardware and software designers to implement different kinds of security mechanisms. The other point that is quite important is that ARM, say, TrustZone allows a diverse range of secure system architectures to be implemented. And that point about diversity is quite important. Unlike something like Trusted Platform Module, TPM, which is a kind of a point solution for security, it provides a well-defined set of crypto services. TrustZone gives you something that can be used in a much, much wider range of applications and approaches to trust and security. So it gives you much more design flexibility, both from a hardware and a software point of view. And that does have some advantages and disadvantages, some of which we'll touch on later in this presentation. Just as an example, the project that I worked on using TrustZone would not have been even remotely possible to do using TPM. So it does open up a huge range of different design approaches. TrustZone is supported by a number of ARM CPU architectures originally introduced on the ARM 1176, which is getting a bit long in the tooth now, probably not really used these days for new designs. The Cortex-A series is very much the current set of CPUs that supports TrustZone and could be used for embedded system design. And ARM V8M is a new architecture that ARM recently introduced that supports TrustZone. Actually, the implementation of TrustZone depends a little bit on the actual CPU design as well as the architecture. My project, as I said, was using Cortex-A9, so everything I'm going to say today refers specifically to the A9 implementation of TrustZone. I know that the processors using the new V8M architecture will have a different implementation, so some of the detail that I talk about won't apply. I'm not going to be talking about V8M architecture at all today. Okay, here's a kind of top-level view of what TrustZone gives you. This is a diagram that comes from ARM. I think it's quite a good starting point to understand TrustZone. And the first point that it makes pretty clear is that TrustZone is not a crypto coprocessor like you could consider TPM to be. Instead, TrustZone has a completely different approach. What it does is it lets you divide the hardware and software design of your system into separate partitions or worlds, as the terminology has it. So one of these worlds is trusted and runs only software that's known to be secure. And the other world is not trusted, and that's where any old software could run. You'll probably also see the terminology that calls these secure and non-secure worlds. So I think I use that terminology in this presentation as well. So you might, for example, have a hardware crypto engine in the secure world where it can only be accessed by software that's trusted and known to be secure. And actually, that's how a TrustZone-based design might emulate TPM, I think. So a really important point is that the actual hardware of your system is also partitioned between the secure and non-secure world. That means software running in the non-secure world can be completely prevented from accessing hardware that's supposed to be used in the secure world. In general, software in the secure world can access all the system hardware, but software in the non-secure world only accesses a subset of the hardware. That's really the way it tends to work in practice. So the system designer has to partition the hardware and the software between the secure and the non-secure worlds. That's not tied down by TrustZone itself. TrustZone just provides the mechanism to do the partitioning. And we'll see later what it means from a practical point of view. How do you actually do that partitioning? And TrustZone also provides built-in mechanisms to make sure that the non-secure world can't accidentally or maliciously gain access to the secure world. That's done by providing very limited and tightly defined ways to get from one world to the other. And we'll see what those ways look like in a few moments. Finally, on that diagram, you can see that there is a debug block, and that debug mechanism and in fact the debug tools that you use must know about TrustZone, and it's very important that the debug tools have the ability to not only be aware of the fact that TrustZone is implemented on the processor, but also give you mechanisms to distinguish between secure and non-secure worlds. That might not be obvious immediately, but I think it'll become a little bit clearer as we work through the rest of the presentation. Well, that's what TrustZone gives you in principle. In practice, how does that look? This is how it might look in a practical implementation. This shows you how the hardware of a system on chip, like the Altera Cyclone 5 or Xilinx Zinc, might be partitioned using TrustZone. So you can see that the diagram is really split into two parts. There's the normal or non-trusted world on the left-hand side and the secure or trusted world on the right-hand side. And at any moment, each CPU core is in a state where it's either in the normal world or it's in the secure world. And that state is actually determined by a bit in the secure configuration register, which is what you can see at the top of each block. That NS bit, non-secure bit, if that bit is set, the CPU is in the non-secure world. If the NS bit is clear, then the CPU is in the secure world. Now that NS bit in the secure configuration register is completely different to the concept of privilege level. So let's say that the NS bit is set and the CPU is in the non-secure world, then the CPU could still either be running in a user mode or a privileged mode. The NS bit itself doesn't necessarily control that user or supervisor distinction. Okay, the other important factor in this diagram that you can see is the hardware that the CPU can access depends on whether it's running in the non-secure or the secure world. So if you look at the right-hand side, the secure world, you can see that the CPU in secure world can access things like the real-time clock, GPIO, I2C, and graphics, whereas in the non-secure world, the normal world on the left-hand side, it can't access those peripherals. So in this particular system design, the RTC, GPIO, I2C, graphics, etc. are considered to be secure devices. They can only be accessed in secure world. And correspondingly, there happens to be a set of I/O devices in this design that are only accessed in the non-secure world. So that's things like Ethernet, USB, and so on. It's also true, although it's not quite so obvious from this diagram, that some registers are banked between the non-secure and secure world. You know, ARM has this concept of banked registers, where there are multiple copies of the register, and which one you access depends on some of the state information. So that banking mechanism applies to some registers, depending on whether you're in secure or non-secure world. And some of the registers in the MMU and the interrupt controller are examples of that, and we'll talk about that later as well. And lastly, if you look at the RAM sort of pretty much in the middle of both of those blocks, you can see that the system memory is partitioned so that some of it's accessible in secure world and some of it's accessible in non-secure world. So I said a few moments ago that the system designer can design how the hardware is partitioned between the secure and non-secure worlds, and that's true in general, but some of the decisions might be baked into the design of a system on chip, such as the Cyclone 5. If you're familiar with the Cyclone 5 hardware, I'm talking specifically about the L3 interconnect on that hardware. So that means that the system on chip design can actually have quite a large impact on the actual practical usefulness of the security features that TrustZone promises in principle. And again, that's a point that we'll come back to a little bit later, and I'll give you some examples of that. Okay, so we have this concept of the two worlds, the secure and non-secure world, and we know a little bit about how the partitioning works between worlds, at least from a hardware point of view. And the question is, how does the CPU then get to make transitions between the secure world and the non-secure world, or vice versa? And the important point to remember here is that the process of getting into secure world is all controlled automatically by the TrustZone hardware, and there are a very small number of well-defined events that allow the CPU to get into the secure world. So, for example, in the ARM v7a implementation of TrustZone, the only way that you can get into secure world is by some sort of exception. That's one area where the TrustZone implementation for V8M is a bit different. It has a more efficient mechanism, which is probably better suited to embedded systems for getting in and out of secure world. So let's go back and focus on the ARM v7a implementation of TrustZone that I'm more familiar with. The way this works is like this. So the CPU always starts running in secure world after a hardware reset. That makes sense because there has to be some software that starts up the system and establishes the security mechanism. So that's fairly straightforward. Then at some point that software will hand over to run code in the non-secure world. And the question then arises, once you get into non-secure world, how can you get back into secure world? And the answer is really by a couple of mechanisms. First of all, there's a thing called the secure monitor call. That's a special instruction which works a bit like the supervisor call instruction that user mode code would invoke an operating system service with. In this case, the secure monitor call allows non-secure code to invoke services in the secure world. And when you execute that, when you have some non-secure code which executes that SMC, secure monitor call instruction, it causes an exception, and that exception is always handled in the secure world. So it makes a transition from non-secure to secure world. It's also possible to configure the processor to handle some other exceptions in the secure world. So interrupts and data abort exceptions in particular. And for example, in my project, I configured the processor so that FIQ interrupts, the ARM fast interrupts, were handled in secure world, but ordinary IRQ interrupts and data aborts were handled normally. There's a processor configuration register that allows you to set that up. And that can be configured during startup by the secure software. So those are the mechanisms that you can, that TrustZone allows for for you to get from a non-secure mode into a secure mode. What about when you're in secure mode? How do you get back to non-secure, the non-secure world? Well, the answer to that is that that's really a software-controlled process. There's a simple but well-defined sequence. You have to manually set the NS bit in the secure configuration register. That's the bit that we saw on the previous slide that defined which world you were in. And then you have to perform a return from exception, and that's how you get from secure back to non-secure world. So there's a very simple state transition diagram which illustrates essentially what I've said in that slide, that the most important point really is that the only way you can get into secure world is through some sort of hardware controlled mechanism, which is essentially an exception. Excuse me. Well, let's look in a bit more detail then at the typical flow of control in a system that's using TrustZone. As I said, the CPU always starts executing in secure world after a reset. So you might expect it to be running some sort of secure, trusted software. It might be a bootloader or something that will initialize the security mechanism. So that might include partitioning the hardware and the software resources between the two worlds, if that's to the extent that that's actually configurable depending on the SoC. It might then load the non-secure code into a non-secure region of memory. That would be typical of a bootloader to do that, for example. And then it would set the non-secure bit in the secure configuration register, and it would perform that return from exception. And that's essentially the kind of handover to the non-secure world. So that return from exception would have to be kind of manually set up so that when the accept and return happens, it enters it goes to the entry point of the code that you want to run in the non-secure world. And so that could be an operating system, for example. The non-secure software then would initialize itself, and at some point you would expect that it would need to invoke some services from the secure software. And in order to do that, it executes this SMC instruction, secure monitor call, and that would cause an exception. And that exception takes you into the secure world, and it would execute a handler in the secure world. And that handler would have to identify the service, carry out the service, and then it would go through this procedure of setting scr.ns and returning from exception, and that takes you back to the non-secure world. And that cycle, of course, could repeat many times during the life of the system. Incidentally, when that return from exception occurs, the software in the non-secure world just continues executing at the instruction after the SMC. And one thing I didn't say before is that that SMC instruction allows you to pass data from the non-secure world to the SMC exception handler that's running in the secure world. So that could be in general purpose registers, and there's also a 4-bit field in the SMC instruction opcode. So one way or the other, you can use that as a way of identifying the service that you're requesting and possibly passing arguments to it. Okay, if you've been following closely, you might have spotted a possible flaw in this scheme. I said earlier that the sequence for getting from secure to non-secure world was to set scr.ns and then do a return from exception. But you might be wondering, well, if setting scr.ns immediately causes you to be in non-secure world, how does the return from exception actually work? You know, aren't you already running in non-secure world as soon as you set scr.ns? And the answer is that you would be, except for the fact that the processors that support TrustZone have a special mode called secure monitor mode, and this secure monitor mode is there to act specifically as a kind of gateway between secure and non-secure worlds. So this mechanism of setting scr.ns and then performing a return from exception is designed to work when the processor is in this secure monitor mode. So when you issue an SMC instruction in the non-secure world, the exception is taken to secure world, as we said, but it also puts the processor into this special secure monitor mode. And that means that when you are going to do the return to non-secure world, you can set scr.ns, and because you're in this special mode, it doesn't immediately take the processor back into the non-secure world. In fact, when you're in secure monitor mode, the processor is always going to execute in the secure world whether or not the scr.ns bit is set. It only goes back to non-secure world when you do the exception return. So that's really critical thing to know about this secure monitor mode is absolutely the key to being able to make transitions backwards and forwards between the non-secure and secure world. What I want to do now is spend a little bit more time talking about the way the hardware partitioning works, because there are several aspects to this which aren't necessarily obvious, and it took me a while to understand what was actually going on. So let me see if I can explain it now. There are several aspects, as I said, and I think it's going to take probably 3 or 4 slides to kind of cover this properly. The first is, if you think about hardware that's internal to the processor itself, the CPU itself, I mentioned earlier that there are some banked registers. So what looks like a single register actually exists as 2 copies, one for the secure world and one for the non-secure world. An example of this is that there are security banked versions of the system control register, SCTLR. That's one. Another example is the vector-based register and some of the MMU registers like the context ID and the translation table-based registers, which really define what virtual memory context you're running in. It turns out that whether you see the secure or non-secure version of these registers is determined exactly by the state of the scr.ns bit. Now, in most modes, that's exactly equivalent to whether the CPU is in the non-secure world or the secure world, as you'd expect. But because secure monitor mode can set or clear scr.ns as it wishes, but the CPU will stay in secure world, what this means is software running in secure monitor mode can see either the secure or the non-secure copy of these banked registers depending on how it sets scr.ns. So that actually can be very useful. For example, in my project, the secure software needed to be able to read and write the non-secure copies of the MMU registers that control what VM context was in place in the non-secure world. So that's the context ID and the translation table-based register that I mentioned. And that can only be done in secure monitor mode because of its special ability to set scr.ns to whatever value it wants without causing the processor to make a transition back to the non-secure world. So that was really important discovery and a useful thing to know, I think. Looking outside the CPU and MMU core, let's talk about how the hardware partitioning affects memory access. The way this works is that when the CPU itself accesses memory, it provides the MMU high-speed memory management unit with a virtual address, excuse me, and a thing called the non-secure tag, which is shown as NSTID in the diagram. So that non-secure tag is more or less a copy of the scr.ns bit, except that it's always 0, which means secure when the CPU is in secure monitor mode. So essentially that tells the MMU whether the memory access comes from secure world or non-secure world. So that combination of the virtual address and the NSTID goes into the MMU, and it translates the virtual address to a physical address. And as we know, the MMU has banked copies of the registers that define how that translation is done. Effectively, you can think of a logically separate MMU for the secure world with its own translations, which are independent of the translations that might be set up for the non-secure world. So the output of the MMU, depending on which set of translations it's using, controlled by the NSTID, the output of the MMU is a combination of the physical address and a non-secure tag, NS. Now, it turns out that for translations done by the non-secure MMU, that non-secure tag, the NS bit, is always 1. But for translations done by the secure MMU, the NS tag can be either 0 or 1, depending on the translation tables. Before we worry about that too much, we have to know, what does that non-secure tag actually do? Well, in effect, it is really an extra bit in the physical address. So in principle, you could think of 2 separate physical address spaces, one for secure world when NS is clear, and one for the non-secure world when NS is set. And in principle, they could be accessing completely different physical memory. TrustZone doesn't define how the NS tag is to be implemented by hardware outside the CPU MMU combination. So it's up to the system on chip design, for example. The way it tends to work in practice, as far as I can understand and as far as I've experienced it, is like this. The memory controller will look at that NS bit and it will say, okay, you're doing a non-secure access. Are you allowed to access the memory at that physical address with a non-secure access? If you are, fine. If not, I'm going to raise an exception. So it's doing a kind of go or no-go check based on the NS bit and probably the physical address as well. If the memory controller says, yes, you're allowed to access the memory, then typically the NS bit doesn't play any part in actually addressing the location in memory that you access. So the physical address means the same thing, independent of the NS bit. It's just used to control access. So going back to the MMU, I said that when the CPU makes an access with the NSTID clear, that means in secure world, the MMU translation can still result in the NS tag being set, meaning that it's making a non-secure access to the physical memory. And why is that useful? Well, that was another discovery that took quite a long time to make. And it turns out that that is really critical to making cache coherency work properly. If you have a system design where secure software and non-secure software need to access the same region of memory. And we'll see exactly why that is in a minute. So the final thing about hardware partitioning is looking at how I/O devices are partitioned. And of course these are memory mapped in the ARM architecture, and that means in general the same mechanism applies that we just talked about for memory. But bear in mind that the I/O devices will see the non-secure tag, and some of them might have special behavior if they directly support the security extensions. What that means is their behavior might be different depending on whether they're accessed in the secure world with NS equals 0 or the non-secure world with NS equals 1. An example of that is the PL390, the ARM generic interrupt controller. That has some registers that are banked depending on the security mode, the NS tag. Another example is that the ARM PL310 level 2 cache treats the NS tag as part of the physical address. So the cache can actually contain distinct entries for secure and non-secure accesses to the same physical address. And what that means is if you have secure software and non-secure software that's trying to access the same physical memory location, you could end up with cache coherency problems. And in fact, that's something that caused me some trouble early on in my project, until I realized that the way you have to handle this is that the secure software needs to set up a VM context, a set of translations that maps the shared memory as non-secure. And that means that even when it's accessed from the secure world, the MMU outputs what looks like a non-secure physical address. And that way, as far as the L2 cache is concerned, it all looks the same, and you don't end up with a coherency problem. So that's definitely something to watch out for, depending on how your system is designed. And you know, this stuff is not spelled out for you, I'm afraid, by any of the ARM documentation. It does take some digging, and I found that the only reliable way to discover this is to search the technical reference manuals for the devices that you're working with. And generally you should search for security extensions, and that's how you find these little quirky bits of behavior. So I want to pull some of this together by showing you a concrete example of the hardware partitioning I used in my project. As I said, I was using the Altera Cyclone 5 system-on-chip FPGA, and in particular the hard processor system. That contains all the components you can see in the big block in that diagram: dual-core processor, the PL310 level 2 cache, controller for external SDRAM, some internal on-chip SRAM, and tons of I/O devices. The HPS hardware, actually the L3 interconnect part of it, which isn't shown on the diagram, allows software to define whether each I/O device can be accessed by non-secure software or secure software only. It also allows you to partition the external SDRAM into a number of regions, each of which can be accessed by secure world, non-secure world, or either. Now, in my project, the secure world was running a kind of safety monitor which monitored the behavior of a commercial real-time operating system, and the operating system was running in non-secure world. The idea was that the secure software would check whether the RTOS did anything unsafe, and if so, it would bring the system into a safe state before anything really bad happened. So the hardware partitioning we wanted to use was that more or less all the I/O devices were accessible in non-secure world so that they could be used by the application and the RTOS. And I configured the on-chip RAM to be accessible in only secure world because that contained the code of the safety monitor, which was executing in secure world. And I also configured the SDRAM so that part of it was accessible only in secure mode, and most of the rest was non-secure, but it did need to be accessed by the safety monitor, so that's where I had to configure these secure translations to ensure that the cache was coherent. So finally, here are some of the things that I found most surprising about TrustZone, and some hints and tips that might save you the trouble of learning the hard way. First of all, there's no manual for TrustZone as such, rather it's distributed through all of the other documentation. And it's not even referred to as TrustZone in most of the technical documents you need to look at to understand how it works. Instead, you should normally find it documented as security extensions. The PL310 L2 cache manual is an exception, though that does refer to TrustZone, confusingly. As ARM said, TrustZone is a framework rather than a complete solution. So many details that have quite a big impact on your system design, both hardware and software, aren't defined by ARM, but rather by the SoC implementation. So you have to look pretty carefully at the documentation for the SoC to decide how TrustZone meets your needs and how to use it in practice. As we said, there's potentially a problem with cache coherency that you need to think about if you're using shared memory between secure and non-secure worlds. And lastly, but perhaps most importantly, I really wouldn't have had a chance of making my system work if I hadn't had a really good debugger like ARM's DS5 that was aware of the security model. So DS5 knows how TrustZone works, which means, for example, that it can distinguish between secure and non-secure memory, and it can show you the correct values of security banked registers depending on scr.ns. And that really is absolutely vital. I can't stress that strongly enough. Let's try to just summarize then before I close. So TrustZone is a very clever framework for building secure systems, which gives you a lot of flexibility for system design. It can be used to provide traditional security services, a bit like a TPM, but unlike a TPM also allows you to build things like hypervisors and safety monitors that can run safely without fear of being corrupted by untrusted software. I found TrustZone to have quite an arduous learning process with quite a few surprises and quite a few aha moments that I really would have liked to know about in advance. And that's partly because there's no single place where its effect on a system design is documented, particularly not in a very useful way for a software developer. Also, as I said, TrustZone in practice depends quite a lot on the specifics of the system on chip or board design that you're working with. So I'm going to leave you now with some references that will help you learn about and understand TrustZone, and I hope that this presentation has helped sort of break the ice a bit, and you'll find it useful if you're going to work with TrustZone yourselves. I know I've perhaps taken a couple of minutes longer than I'd hoped, but I'm going to hand back to Raphael now and ask if he has any questions from the floor before we finish the presentation.
Yes, thank you very much, Ian, for this interesting presentation. If you have any questions, please feel free to ask us now. Afterwards, we will send you also a short email with the recording of this presentation and webinar. So thank you very much for your attendance, and please ask your questions now or later via email or yes.
That sounds like no questions.
Sounds like you explained everything else great. So if you
or everybody's gone to sleep.
So if everybody, if anyone has any questions, please feel free to write Ian or me. It's no problem. And if not, so thank you very much for your attendance in this webinar. And goodbye. Thank you very much.
Thank you all. Goodbye.